In this lecture, we'll cover the exceptions to the octet rule, including incomplete octets, radicals, and expanded octets. You'll be expected to know these three exceptions to the octet rule and apply them to structure drawing. Let's begin. There are three notable exceptions to the octet rule. We've already seen that certain small atoms will have incomplete octets, such as hydrogen, which forms a duet rather than an octet. The other two small atoms to keep an eye on are beryllium, which forms molecules with 4 valence electrons, while boron atoms are generally satisfied with only 6 electrons in their valence shells. The second exception to the octet rule occurs when molecules have an odd number of valence electrons. This typically occurs as one atom with 7 valence electrons. Molecules with unpaired electrons are referred to as radicals. Common examples are nitrogen monoxide and nitrogen dioxide. Take some time to work through these structures to verify their accuracy, then let's work through an example together. Let's build the Lewis structure for the chlorine monoxide molecule. 1. Sum up the valence electrons. We have one chlorine with 7 electrons and one oxygen with 6 electrons for a total of 13 electrons. This odd number of electrons is our first hint that something is different with this molecule. 2. Select a central atom and arrange the other atoms around it. Since we only have 2 atoms, this step is irrelevant. Move on to step 3. 3. Draw single bonds between the central atom and each terminal atom. Connecting the atoms together with single bonds uses up 2 electrons. We have 11 left to distribute. 4. Distribute the remaining electrons to the outer atoms. Let's add electrons to oxygen first, since it's more electronegative than chlorine. Oxygen gets 2, 4, 6 more electrons. We now have 5 electrons left to distribute. They go around chlorine as 2, 4, and our odd man out, 5. Step 5. Assign any remaining electrons. We used all 13 electrons in the last step, so skip this step. 6. Move lone pairs to create multiple bonds if the central atom has less than an octet. Let's check our octets. Oxygen has 2, 4, 6, 8 electrons. Chlorine has 2, 4, 6, 7 electrons. We're not quite at an octet, but if we shared another pair, chlorine would have 9 electrons around it, which it cannot do. Let's clean up the structure and check for formal charges. Step 7. Verify duets, octets, and the total number of valence electrons. We satisfied octets as best we could in an earlier step. Counting total electrons, we have 2, 4, 6, 8, 10, 12, 13. Checking our formal charges, oxygen comes in with 6 valence electrons, minus 1 from the bond to get 5 electrons, then minus 6 more from the lone pairs of electrons for a formal charge of minus 1. Chlorine comes in with 7 valence electrons, minus 1 from the single bond to get 6 electrons. Subtracting the 5 electrons from the lone pairs and odd electron, we get a plus 1 formal charge. Because oxygen is more electronegative than chlorine, it is appropriate to leave chlorine with 7 electrons. Congratulations! You just worked through your first radical Lewis structure. Our third exception to the octet rule occurs when the central element in a molecule or polyatomic ion is in the 3rd period or beyond, because it can sometimes expand its valence shell beyond 8 electrons. Central atoms with expanded valence shells, also known as expanded octets, can share more than 4 pairs of electrons, which generally results in lower formal charges. Let's see how the expanded octet benefits the sulfate ion. In the structure on the left, all the atoms obey the octet rule, but we have formal charges on every single atom in the structure, including a plus 2 on the sulfur. However, bringing in 1 lone pair of electrons from the top and bottom oxygen atoms to make 2 double bonds minimizes the formal charges, leading to a much better Lewis structure that is far more likely to represent the actual sulfate ion. Let's see how the expanded octet benefits the selenium trioxide molecule. Following the octet rule leaves us with 2 plus 1 and 1 plus 2 formal charges. Making double bonds between selenium and every single oxygen leaves all atoms with a zero formal charge, which is ideal. Let's summarize what we know about Lewis structures. We can finally write out the Lewis structure for any ion or molecule. We know to add or subtract electrons in step 1, and how to choose the central atom based on the number of bonds needed while considering electronegativity in step 2. Step 3 stayed the same. Steps 4 through 6 also stayed consistent. Be sure to pause the video if you need to take notes over this slide. Unfortunately, step 7 has a much longer list of items to check off now to make sure that we have the Lewis structure that most closely resembles the actual molecule or ion. We need to look out for exceptions to the octet rule, minimize formal charges, and ensure that negative formal charges are assigned to those atoms with greater electronegativity. Let's try out this new set of guidelines on an example. Let's build the Lewis structure for the chlorine pentafluoride molecule. 1. Sum up the valence electrons. We have 1 chlorine with 7 electrons and 5 fluorine atoms with 7 electrons each, giving us a total of 42 valence electrons to place in this structure. 2. Select a central atom and arrange the other atoms around it. Chlorine is less electronegative than fluorine, so it becomes the central atom. 3. Draw single bonds between the central atom and each terminal atom. Connecting the atoms together with single bonds uses up 2, 4, 6, 8, 10 electrons. We have 32 electrons left to place. 4. Distribute the remaining electrons to the outer atoms. The outer atoms get lone pairs first, so here goes. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. We still need to place 2 more electrons. 5. Assign any remaining electrons. Chlorine already has 10 electrons around it, but because chlorine is a period 3 element, it can handle an expanded octet. We place the remaining 2 electrons on chlorine. 6. Move lone pairs to create multiple bonds if the central atom has less than an octet. We just expanded chlorine's octet, and the octets of all fluorine atoms were satisfied in step 4. Let's clean up the structure to calculate formal charges. Step 7. Verify duets, octets, and the total number of valence electrons. We satisfied octets in an earlier step. Counting total electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, and 42. Let's check formal charges. The fluorine atoms are all equivalent and come in with 7 valence electrons. Subtract 1 electron for the 1 shared in the single bond, then subtract the 6 electrons found in the 3 lone pairs for a formal charge of 0. Chlorine comes in with 7 valence electrons. Subtract 5 electrons for each of the electrons shared in the 5 single bonds, then subtract 2 more electrons from the lone pair on chlorine. The low formal charges indicate that this is a reasonable structure for chlorine pentafluoride. This table summarizes everything we've learned in Chapter 10 about writing Lewis structures. I suggest keeping it handy while you work problems until the information contained in this table becomes second nature. As always, I'll leave you with the parting thoughts of the authors.